Um, so we'll conclude examples of discrete optimization, and I asked you to do some homework pertaining to brushing up of calculus. So I hope you've done that. So we'll get started with convexity. So this is like the outline of class. We have finished continuous optimization. We'll look at some discrete optimization problems and then move on to actual calculus of optimization applied to n-dimensional vectors. So we looked at some of these discrete optimization problems list. I showed you an example of how parse tree generation for a given sentence could be a discrete problem where you have a discrete search space. Or but I'll look at other examples like feature subset selection, etc. Let me begin with something very visually appealing. Yeah. But before I do that, here's a more exhaustive list of actual discrete optimization problems that get encountered. Map inference and probabilistic models, icing models, I gave those examples, and so on. But all the way to genomics and computational biology. So I listed these in the last class. Let's see some examples today, concrete examples. Okay, so let's take this example where you are looking at segmenting an image. So and correspondence. Sorry, I look at correspondence first. Let's look at correspondence first. So if I'm given two different views of the same object, maybe organ of, right? Or it could be as simple as a house, a building. Our goal is to determine, first of all, what is the correspondence between these two? Now they don't look exactly the same. In this case, you're seeing that there's some parts trimmed off, right? But I want to make sure that I'm able to identify correspondences between those parts, right? It's not necessary that one is just a rotated form of the other. It's possible that there is some skew. There is some scale. There is some. So there are different kinds of transformations. Pitch, yaw, when it comes to 3D, especially videos. Okay. Perspective, right? You look at an object from a perspective, right? So there's a projection that's happening to your on your retina. So we'll see examples of perspective transformations when it comes to convex functions later on. So the problem may not be as straightforward, right, as just determining a rotation. Now you could pose this as a bipartite matching problem, where you could imagine that there is this set you see, which is called U, and a set V, and now basically you're trying to identify matching. Okay, which point here maps to which point here. Now, on what criterion would you do the matching? We have shown some red edges, the edges that we think would lead to a good matching. How do you quantify the matching? Is a question, right? So let's take that example, quantification of matching. And in fact, what I'll do is I'll add an imaginary element S called the source and an imaginary T called the sink. So I don't have colorful chalks here, but I'm just going to use simple depiction. Look at the slide there for better understanding. So in terms of image, you have added an S here and a T here. And S is going to be connected to all the pixels in the image on the left, T is going to be connected to all image pixels on the image on the right. Okay. So T is called the sink, S is called the source. Now, what do we want to do? We want to kind of maximize the flow of information, right? The edges that would give you good capacity would be the edges that you would like to flood with information, flood with signals, right? Flood with flow. So CUV, the capacity of an edge, would be how related are those two pixels. So for every pair of edges, I could have a C, U comma V. So let's say this is a pixel U, this is a pixel V, UV, this is a capacity UV associated with the edge. So I want to kind of utilize that well if I select that edge at all, right? Now, how do you ensure that you don't have one pixel corresponding to both, one pixel on the left corresponding to more than one pixel on the right? So that's where you would need to ensure that the incoming flow is the outgoing flow. You can't manufacture flows, right? What goes out from S is what comes into T. Okay, so you see the equation there. There's some constraints there. For all P is an edge, right? Q comma P is an edge. And so for all P, you need to ensure that FQP, flow from Q to P, is the flow from P to R, right? Where R is an destination vertex. So simply said, let me take some edge here, okay? Some representative edge here. This is my representative edge, P. So what I'm saying is or any Q from which there's an incoming flow to P, ensure that the sum total of all the incoming flow from Q to P equals the sum total of all the outgoing flows from P to E. E is what I used, right? FPR. So these are all Qs, these are all Rs. Is this clear? And then you also need to ensure that the flow from P to Q, this flow from P to Q does not exceed the capacity from P to Q. So F from P to Q is less than equal to the capacity of P comma Q. And obviously the flow cannot be negative. Okay. So these are your constraints. Yeah. So they are pixels. In the case of images, they are pixels. They could also be small blocks you could consider. So the resolution at which you want to do the correspondence is something you need to decide. Now we have subscribed to some level of resolution. At that resolution, we are trying to do the matching. So what would be the capacity? The capacity would be a representation of this representative of the similarity between the blocks P and Q. How similar do they look? Right? Now, again, in that similarity, if you want to do transformations, you're welcome. But you don't want to make that similarity too complex. You don't want to make the similarity itself solve another optimization problem, right? So at the lowest level, you want to keep it simple. Ideally, if you can do it at the pixel level, great. No. So P is, your question is, this is for every edge. So P could be any vertex here or any vertex here. Okay, so you have, I should have put these edges. So both U and V have all their vertices connected to either S, case of U, or to T, right? You're looking at maximizing the flow from S to T. The flow has to go through U and through V into T. Okay, so this P is any vertex in U or V. Is this clear? Okay, so now are there good algorithms for helping solve these problems? It's a max flow problem, right? You're trying to maximize the flow, summation over ui. See this, right? Summation over ui and u of f of sui, which means you want to maximize the flow on all across all edges from s to u. Because that's the same under these constraints, that's the same that will reach t. You can do this, or you can also do a similar thing, right? Maximize the flow from v to t. Under these constraints, they will be the same, right? So now it turns out that there is a for maximum flow problem. Okay, so it's a very interesting problem and how it ends up iteratively finding basically something called an augmenting path. The path is basically a path from the source to sink, so S to T, but you need to create a residual graph. Okay, it's interesting. Just make a note for Fulkerson algorithm. This is an example of correspondence. Let's look at the next example, which is the example of image segmentation. So the second example, right? Image segmentation. So let me motivate this better. So while on the board I take an example of an aeroplane, let me take a slightly different example here. Could be just simple lotus. Okay. Now I want to make sure that the example on the board is just an aeroplane, which is kind of monolithic, doesn't have very narrow areas. But this lotus, for example, will have a stem. Okay, stem is actually green. It's green. So objects need not be monolithic like the aeroplane. Now, what we are trying to do there is we're saying, okay, if there is an image here, on top of the image, I'm going to top here, or put it here also. I'm going to again create some kind of a source similar to earlier. So I'll list S, and there's going to be a T, which is a sink. But now I'm looking at a different problem. Okay, so my problem is as follows. While I'll still look at, from each T, from T to each pixel, I'll have these edges. Likewise from S. I'll also have edges connecting, neighboring pixels. So imagine, creating a grid. Okay, very, very refined grid. And now every pixel here, you can see that this pixel here is connected to some pixel here. We'll make it very small. Can make it very small. So this pixel is connected to this pixel. This pixel is connected to some other pixel here. So there are several edges in this image which correspond to edges on the grid. Right? What we want to do in the case of segmentation is that the areas that lie inside the image should have higher pixel similarity, right? In contrast to areas that lie outside the image. However, you need to remember, unlike that aeroplane, you may have a stem or something like that, right? Maybe thin areas. So you need to ensure that you account for cases where you're actually foraying into other regions of the same image, which may have which may be another connected component. The stem itself is a connected component, right? But the area bordering the stem and the flower is probably the tricky region. Likewise, in the aeroplane also. I mean, it's not that the aeroplane is that easy. Even here, you'll find there's a tail, right? You need to ensure that the tail, the joints, etc., need to be properly catered to. So let's see how we tackle this problem. So we have created a foreground and a background in this simple case. In the case of Lotus, it's not going to be just foreground. Foreground itself has different components. So CUV in this case is say difference in grayscale RGB values. Create a cost. Now, the way we are going to use these costs is slightly different. We are saying that, well, I want to ensure that the intra-point similarity, similarity of points within the object is higher than the similarity of points outside. So you basically, let's say CUV is difference in grayscale RGB values. Sorry, this should be min. It should be min, I think. Yeah. In this area, this. Okay, so what are we looking at? For every point in S and every point in S complement is nothing but the space of all V's, which is all the points. From that you subtract S, that's S complement. So with V is all the pixels, right? So S, V minus S. So you want to make sure that for every point every edge that goes from S to S complement, the sum of all the edge costs is minimized. Coming back to this example. So this makes sense for the pink region, right? This is S, this is S complement or V minus S. Now what do you do with the stem region? There's going to be similar. This is something we want to be part of S. I don't know what is S. S is basically that which belongs to the foreground. And V minus S is what belongs to the background, right? So you're trying to push some things to T, some things to S. How would you handle a narrow region like the stem? How do you ensure that the stem doesn't go into the background? For aeroplane case, it looks easier, right? Sorry? Differentiate. I'm talking about designing the objective function. So in the objective function, you'll have a differentiation. How do you design an objective function which accounts for lean regions like the stem? Okay, so that's a good suggestion. Smaller. Oh. Smaller cell sizes. To help address. Okay, what else? What else can you do? Search vertically. I don't think that's going to matter, right? Because it's all the edges in UV. So if you make it longer, the resolution smaller, you should consider both vertical, horizontal, everything. Yeah.
UV can just be getting the different pixel values.
But that we are already doing, right? Say cost difference in grayscale RGB values. of the 2 pixels. So that's already done. Could you also consider something relative? So just difference is not good enough. You could also consider some context. Position, okay. Okay. So the other point is you can also consider, so CUV, address this, could also factor in neighborhood RGB grayscales. So what does it mean to factor in neighborhood grayscales? Well, I look at if my current pixel is green, and if I go exactly to the neighbor, I land up in some water, right? That could be the background. And I do that for the next pixel as well. So even if it doesn't look completely green, if it is different from its background, I should connect to it. Right? So somehow I need to factor that in. So while we try to make this a very pixel based cost, in practice it may not just be pixel based, pixel in its neighborhood based cost. How exactly you design, we are not getting into details. Okay. Now again, why one would help, because if I'm in a thin region and I look at its neighborhood, it's all brown, thin region or green region, its neighborhood is all blue. There's another thin region, which is say yellow, it could be a yellowish patch here, right? Or it could actually be leaning from the pink one. So its neighborhood is pink, but it's, sorry, it's the other pixel is pink, but its neighborhood is again blue. So both of them stand out in contrast to their neighborhoods, right? So they may connect together. So you have designed the CUV little expertly. This is engineering. It's beyond optimization. I'm saying you can push some of this headache into the design of CUV. Okay. Yeah, so that's what I said. I mean, limitations are that, you have not accounted explicitly for the homogeneity of S. So this is not sufficient. So the stem itself is a very homogeneous thing. We have not looked at that itself. It's just reduced to pixel-based similarity. I've written that as a limitation. Is that okay? Okay, so how do you think this can be optimized? So this is a min cut problem. I want to minimize the cut. So there's another problem, which is what we discussed earlier, maximizing the flow. They are kind of related, right? So maximum flow problem can be, the problem above can be solved in polynomial time. So you can solve the min cut problem using the solution to the solver to the max flow problem as a black box. So if you know what is the max flow, you can derive the min cut. Okay, so think about it, how you do that. Just leaving you as a homework problem. Yeah. So I want to find an S such that within points in S, wait a second. Oh, sorry, this is max. So this objective is max, but what you're looking for is min cut. No, you're right. Actually, this is still a max flow problem. So I'm in fact answering my own question here, homework problem. That's true. There was the reason I had written min here. Yeah, this should have been max. You're right. Because you're looking at in the way I have written it, you're looking at identifying all those points S such that if you go from S to S dash, the cost is maximized. Right. So this is kind of looking at max cut here, but you can also There are also min cut. You can post it as a min cut problem. How do you post it as min cut? This is max cut. What's the min cut issue? So instead of cost, I might look at, so C is basically difference, right? But if I look at similarity, then what would I do? Sorry? So you would look at minimization. If you're looking at similarity between points, then I want to look at the min, right? Yeah, so where I posted. So you have an answer to this question, right? So already, how do I derive min cut from max flow? Okay. So again, I repeat, this was solved with cost. Okay, let's take a different. So instead of cost, let's say I looked at similarity. Say similarity in grayscale values. Okay, so for some reason, I can just replace a CU, C with S. And now let's say I have the same objective, but yeah, I'm looking at min. Could I change something else? Yeah, this is fine. Okay, so this is actually the min cut. So you can clearly see there's some relation between the two, right? If I were to find max flow, I could also determine the min cut. Okay. So Ford-Fulkerson algorithm is for determining the max flow there. Can I use that polynomial time algorithm as a black box to determine my min cut? Okay, they are related. So I don't want to spend more time. This again, this is lot of it is just algorithms, but relationship between objectives is interesting to explore. A second example of discrete optimization problem is feature selection. So you're given variables x1, x2, xn, and you're given a class variable y. So what you want to do is find a subset of features which are representative of the class. So I, x1, x2 is the mutual information between the variables, which means okay, I mutual information I can define. Mutual information between x1, x2 is the entropy. This, as you would have come across, discrete entropy, say of x1, the entropy of x2 minus the joint entropy of x1 and x2. Okay, so this is denoting how basically similar are x1 and x2. Okay, so H is a measure of uncertainty. So uncertainty of x1 plus uncertainty of x2 minus the joint uncertainty in x1 and x2 is telling you, well, how much is the certainty of x1 and x2. So it's like saying how well correlated x1 and x2 are. H is entropy, measure of uncertainty. Okay, so what is the problem? Select a subset of features such that the subset of features is as good as the original set. So I want a subset of this X, which the original features are all A. I want a subset X such that they are as good as the original set. Now, obviously, I would like to do this in a very targeted setting. Targeted setting is from the perspective of a particular class. So if I'm trying to determine what are representative of the lecture complex classrooms as against say VMCC classrooms. So I might want to find a color of wall, but I don't probably need color of wall and ceiling and floor, all of them, right? Maybe one of them is good enough because they seem to be mutually correlated. It's very unlikely that you would have color of one wall as blue and the floors in green, right? They're not correlated. It doesn't look good. So given correlation between the random variables, you might want to just select subset of them. From perspective of class, that's very important. So there's an optimization problem. So now what I've done is instead of the random variables, I posed the optimization problem in terms of the class variable. Same mutual information, but measured for a subset of random variables XA and their association with the fixed class variable A is that the size of A is less than or equal to K. The features here are discrete, yes. So in PCA, we were looking at continuous valued features. These are discrete valued features. So this is a kind of discrete counterpart to PCA. Yeah, good point. Yeah. Okay. So now it turns out that this function has some nice property, especially if you assume that the random variables are conditionally independent given y. Okay. So how many of you have heard of the naive-Bayes classifier? So naive-Bayes classifier, what does it assume? What is the naive-Bayes assumption? The probability of x1 comma x2 given y can be decomposed as probability of x1 given y into probability of x2 given y, right? Yeah. Size of set A, that's a cardinality. Should we divide I of xa comma y by the size of the set?
We take the set A and we take the set containing the set A. Set A1 which contains the set A. A1 will have more information.
True. So I think your point is, isn't I a monotonic function? Won't it just keep increasing, or it will certainly not decrease as you keep adding, right? That is exactly why this cardinality is important, right? If I say size of A is less than or equal to K, when I want, let's say I add supersets which are not as informative as some other superset. So I would pick those supersets which are more informative, if at all, right? So that's why cardinality constraint is important, especially if I is monotone. Monotone means increasing or not non-decreasing as you increase the size set in its membership sense, not just size, but membership as well. So good point. Okay, coming back. So it turns out that under naive-Bayes assumption, under this naive-Bayes assumption, I, mutual information, has a nice property which looks like this submodularity. It has this diminishing returns property. Okay, so this is submodular Submodularity is like concavity under the naive assumption. Now, those who have seen naive classifier know that it works even in several types of practice, even when the conditional independence assumption doesn't necessarily hold. So it's a very it approximate, approximately adhering or complying with naive assumption is also good enough for classifiers to be effective. So likewise, you can use this property. Now, if it's submodular, it turns out that there are some nice algorithms which give you good solutions. May not be optimal, but good enough solutions with some guarantees as well. Okay, so that's the reason they behave like concave functions when it comes to finding points of maximum. Is this motivation clear? Okay, so yeah, the second part we'll see more of concept of submodularity. There's a whole bunch of open source modules we have put out under Decile, which I talked about trust earlier, right? So we can also look at our publications, which leverage mutual information, but applied not necessarily to entropy, but to other submodular functions. Like I showed, imagine replacing this H with some other interesting set function. Then you can have mutual information variants of those other functions. So, and we'll see some more examples. You can have generalizing H to other submodular functions. Using some interesting property. So you can look at mutual information based on other lens. So entropy is just one lens. Entropy is one lens of measure of a set and its uncertainty. And entropy turns out to be a canonical example of submodular function. That's the other interesting part. Okay, the third example is training data subset selection. I gave this as a motivation earlier, but now looking at it a little bit more carefully, which is if I have training data set and a budget K. Okay, so I want to be able to select a subset of size K of the same set S. Let's call it SK. But what do I want from that subset SK? I want to ensure that a model that is trained on the subset gives me performance that is comparable to a model trained on the entire set. Okay, so I have the largest set S and a subset SK. So there's a performance of model based on the smaller set. I've just given it a name performance, but you can use it. You can actually compute the performance in terms of the parameters that optimize the loss function. So you want the performance on SK to be similar to the performance on S. Now, how would you do that? Well, one way which I've suggested here is, and it's a very intuitive thing, right? If I'm trying to discover this SK, how about looking at the gradients? The gradients, I introduce what's a gradient. Obviously, we'll see a lot more about gradients. Gradients give you an idea of how the function is changing, right? So look at how the function, the rate of change of the function at some intermediate point of the learning on SK and the rate of change of the function at some intermediate point of the learning on S and see how close they are, right? So could that be a proxy into what that right SK should be. Right? So now it's a you see it's a bi-level optimization. Why is it bi-level? Why is the word bi-level used there? Anyone? What is bi-level here? Right. So you're saying argument over all possible SK of this performance, right? Distance of the performance of SK and performance in S. Where this performance itself is what? Using a set S, if I have to compute performance, what will I do? I look at yes, some measure F score, or we would even look at the loss, right? Let's look at the loss. Loss, but computed with respect to what parameters? Loss on S computed using argmin over theta of, right, the same loss function, look at L theta on S. So this performance is indirectly requiring you to compute the optimal parameter for S. If not optimal, at least approximately optimal. A good estimate of the optimal parameter with respect to S. Right. So I need to find a theta, then compute the S, and then I have to find the SK which matches the S in the sense of performance. So you can see there are two levels of optimization. There's here argument and argument here. That's why it's called bi-level. It's a very grand problem. As I said, if you look at something like gradients, you can look at specific instances which might have more tangible solutions. Otherwise, this is good to write on the board, but what will you do? How will you go and write code for this? Okay, but this is an instance of training data subset selection. Right, so this is a goal. This has actually become critical for self-supervised learning. Like if you want to do pre-training LLMs, it's become very important. As I said, very often you have a bunch of data points or documents being repeatedly scanned for pre-training. Which are the documents that are worth scanning? I tell you, this is a very important problem if it can be solved efficiently. Can the structure, right? If your documents, pre-training documents are coming from Wikipedia, could the structure there be exploited if one is a superset or more general document than the other? Could there be some curriculum that you can come up with? I've not even talked about those, right? So there are other associated problems. Could there be a curriculum on this? It could be that one document here more general than another document here. An auxiliary info such as relationships. Between elements of S, we exploit them. In a curriculum sense. Okay. Yeah, and this also makes a lot of sense when the labels are missing on some or all of the given data points. So if you're missing labels, then there's even more need for curriculum. Right? And here's an example. It's called of label efficiency. So what I do here is I'm looking at, okay, what are the documents that I should label in the first place? What are the examples, subsets of V, which I should label in the first place? So now I'm looking at, again, the same notion, but the uncertainty can be viewed from the point of view of if those examples are labeled, the loss will behave better. There'll be better stability in the loss. And so on. Okay. So yeah, V denotes the distance, such as scale divergence between two labeled data sets, or you could also look at gradients. The optimization problem is basically minus of D, XA, XV to be maximized. Looking at some distance to be maximized, my negative of the distance to be maximized. Basically, you want to minimize the distance. Okay, so again, the submodlib library gives you a whole range of options here, but it's not just submodlib. There's also the chords, a whole bunch of algorithms implemented in our chords library, core sets. And now we just got a ICLR paper accepted. In fact, I'm very happy to share that uh, a project from the previous year's CS769, right? It got accepted at ICLR, and that was all about core sets. Okay, core sets in a federated setting. So Pratik Chand, who did his project last year, he continued on it. So that's exactly core sets learning core sets. But it was in a slightly more challenging situation where you have federation, where the clients are not supposed to talk to each other directly. So, right, you may have this same problem, but imagine you have not just one S, but multiple S's. Okay? And you want to identify the subsets from individual clients towards better generalization. It's not just efficiency, it's also for better generalization for robustness. That's true. I mean, if you've seen Mixtral, which has fewer parameters, sometimes more robust than something as I think Llama's 30 billion or whatever model, right? They have benchmarked. So likewise with data sets as well, data sets size. Let's look at the next application. So if you have questions, let me know. The fourth application, the last application we're looking at for discrete optimization. And this is it's easy, we can close it soon. So we talked about the k-means algorithm. So in the case of k-means algorithm, we are trying to identify clusters and memberships. Okay? So we had points and we needed to know whether this point should belong to this cluster or this cluster. But a big issue with these clusters is that their centers might not correspond to any of these points. Okay, so let's give different colors. So this is orange and this is blue. So it's a blue cluster and an orange cluster. And you wanted to assign points. And these are the cluster so-called centroids. The problem in k-medoids is slightly different. So given a set of data points, a similarity function, you're told, okay, how similar is each point to each other point? Can you do the following? Can you assign points to the clusters such that the cluster centroids are actually practical, tangible points? Okay, I don't want these centers to be necessarily means. They could be what we call midoid. You understand what's a midoid, right? So they should correspond to actual points in the clusters. So here's an example of middoid with k equals 2. Right? The problem is that k-means might not coincide with any data point, whereas middoid has to coincide with the data point, one of the data points. Okay, there's a facility location problem I talked about earlier. So if I have facilities to be set up, right? Facilities could be malls, facilities could be shopping complexes, right? In cities, which city would I set up a facility, or maybe towns, neighborhoods, towns or suburbs? Now you can't say, locate, let's say there are two towns, one on each side of each bank of a river. You can't say have the shopping complex in the middle of the river floating. Obviously, right? You need some concrete feasible location. So these points are feasible locations. Obviously, if there are two equally sized suburbs on two sides of a river, you may have to choose one of those. But if you had three, then you may choose one of these three, which kind of helps minimize some cost function. So what is that cost function you would look at, right? So Sij could also be, a similarity could be the negative of the distance. I say, so this might be negative of distance, okay? The negative distance. Okay, so you want to act subset of points that can act as a k-middoid. How do you go about solving this problem? Any thoughts? How do you write this last optimization problem? Let's write in terms of similarities. So what will I do? I will do a summation over so I want to determine some set of facilities, right? So find A. I want to do some A. My search space is A, and the size of A should be less than or equal to K. So for every point in A, I want to find the closest facility, the best facility. So what will I write here? You need to help me fill up the blanks. Should it be a max or a min or a sum? Okay, let me in fact leave it open. I'm writing some of the indices. So there is a I summation, I in the set V. So V is at all the elements. A subset of V, J in A. Okay, so help me fill up these blanks. What do you think will be here? Two blanks to help me find the solution. Second one will be max. And the first one. So what is the second one doing? Saying, okay, for each point in my final facility, set of facilities, for each point in my set of cities, across all the facilities, I'll find the most similar facility. Right? So this is saying for each point in the set of cities I have, pick the best facility. And then what do I want to do with respect to all the A's? What kind of facilities do I want to pick up? What kind of k-middoids I want to pick up? This whole thing should also be again maximized. You understand? Right? So max over A, max over Sij, a summation in between. Okay, so just to kind of help you visualize this again, what is this yellow part doing? Any point I is assigned to the middoid J, which is most similar to it. That's what the yellow part is doing. What is the red part outside max doing? It's searching over all 2 raised to n possibilities, the overall power set elements. Search space the power set. That power set which maximizes the facilities, set of facilities which cater to all the cities as well as possible. Under the similarity measure, the similarity itself could be rich. The space of similarities could be rich, including gradients of loss functions, similarities based on gradients, dot products between gradients. So can be a part of a larger scheme. Okay. Yeah. So this facility location I said is related to some again some modularity. This is a submodular monotone submodular function. Okay. So I think we've seen enough examples, and I hope you have developed some confidence in understanding, parsing objective functions in machine learning. Right. The whole this part of the code was to really get you into reading papers. You should be able to now embark upon seminar papers. I hope as many of you have chosen seminar papers as possible. How many of you have chosen seminar papers as yet? Oh, that's good. So looks like pretty much everyone has. If you have not, do pick up as a form that was said, right? So, so this is the space we have seen so far. Continuous optimization, some problems. Discrete optimization, some problems. Some we saw in the mixed continuous and discrete optimization space, right? Like hard k-means, data subset selection is mixed continuous and discrete optimization. Data subset selection is clearly mixed because this parameter learning, the bi-level optimization, right? This is continuous. Right? The inner optimization problem is continuous optimization. The outer optimization problem is discrete. Though in areas such as core sets, they make even the discrete into continuous, like our ICLR paper from last year's CS769 project. It's a totally continuous optimization problem, where instead of learning the sets, we learn weights on elements in the set. So that's an area called core sets. So most people do that. They relax discrete into continuous. But sometimes it makes sense to be discrete because that's when you can also get interpretability. So we saw some examples here. Then continuous, we saw concave functions which exhibit diminishing returns as examples of maximization functions. But convex functions basically are negatives of concave functions. That's one way of viewing it. And they've been more studied, largely because also the area of convex functions and convex sets are closely related. So we'll talk about convex sets next. Okay, so summing up, so far we have already done this. Basics of continuous optimization, vectors, matrices, gradients, Hessians. Everyone brush that up. I had posted slides, right? So please ensure you're brushed up. Everyone did, right? So you should get comfortable. And that's why I gave you some lead time. So, deriving gradients and Hessians, practical aspects, implementing loss functions and gradients in Python. So that's also not difficult. I gave you some collab notebooks already, right? Where you could actually write using NumPy. Your first assignment is going to come up where you will have to just write some of these programs. So next week, we'll put out the first assignment. That'll take care. Okay, so now, so we saw enough motivation, how to pose optimization problem, matrix algebra, but now we'll actually start looking at how algorithms work, right? What is the basis of these algorithms? At least some of these algorithms. In the seminar reading, we'll do many more. And yeah, 70% of projects I've worked with industries, it's invariably about posing optimization problems. Okay, so there's no way you can escape that. So yeah, this is going to be really quick, super fast. Now we'll talk about convexity, gradient descent, projected proximal gradient descent, subgradient descent, right? And then we'll talk about I don't know how much of Newton and Gaussian-Newton we'll talk about. I'll put slides. Whatever I don't cover in the class, I'll post them as optional reading. So typically only that which is covered in the class is mandatory for exams. So some like coordinate descent, Frankfurt will certainly be more optional reading. And if it, so another thing is if it comes up in one of your paper readings, then we'll try and clarify it as well to the extent that's possible for the entire class. Okay. So yeah, this is discrete optimization. Some of these topics we'll talk about. Matroid, spanning trees, and so on. Some modularity and convexity. Some of it will just be optional reading again. So as far as continuous, we'll begin with continuous optimization, and we have seen four broad areas: supervised learning, unsupervised learning, contextual bandits, and recommender systems. Right? This is like another classification or bucketing of the applications we have seen so far. So if there are doubts on what I have given as homework, do let me know. And if not, then we'll start looking at. So this is what I had asked you to brush up, right? For today, vectors, matrices, vector product, matrix, matrix, matrix product, and some illustration. So and then I'd given you some homework on derivatives, right? So and partial derivatives, which are important for composing gradients. So okay. So any questions on this homework exercise? And I'd left a small note, right? For some problems like this hinge loss, we may not have the requisite machinery, requisite equipment. We'll deal with that in a couple of classes. But all others, you should be able to compute gradients. Okay, that's our first exercise. So these were the four, right? So everyone did this? Regularized logistic regression. How do you compute? So I have kind of helped study this, right? So lambda by 2 norm w square, that's a regularizer in logistic regression, plus summation I equals 1 to n log of 1 plus exp minus wi w transpose xi, yi w transpose xi. So the best thing is to write down. Right? Okay, you write down the components. It's okay if you have to sometimes expand a vector into sum, right? Dot product between two vectors into sum, right? It's okay. Go through that hard grinding exercise of writing, which unfortunately I shouldn't be sparing too much time for in the class. Okay, so this is what we have done. We have just sent exp of minus of yi w transpose. So this part in gray is where I've expanded what this looks like. Okay. So now if you were to take a gradient, so what is our goal? Our goal is to compute the gradient of this loss function. How do you compute the gradient of a log of an exp? The gradient of the first component is easy, right? Gradient of first component is what? Partial derivative of norm w square, which is nothing but norm w square, 2 norm w square is easiest. Is the sum of the squares of the components. The partial derivative will just be 2 times the corresponding wi. So that's very easy. And because it's lambda by 2, I'll just get lambda w here. This part is clear to everyone? This part in blue? Should have no doubts at all. So if at all you find something challenging, it will be this part. So I've tried expanding here. What do you get here? So exp. Okay, so let's look at just this part. Right? Okay, I'll look at. I've written it in the next slide. Okay, this is the simplest of all. The partial derivative of summation w of minus summation wj xij yi with respect to wj will mean that only the corresponding xij and its yi will survive, because wj would be none of the other components which involve wj primes have dependence on wj. Is that clear? Okay, so now if I add an exp, what happens? There's a gray part. Okay, now go back. So I add an exp, then what happens? This is an exp here, right? I've just expanded on this the next slide. exp of this summation. So only exp will remain as it is, right? So only the corresponding yi xij will come out. Exp otherwise will remain as it is. This blue part will remain as it is. Okay, that's why I've used color coding here. But then what happens to the log of 1 plus something? Chain rule, right? You'll have 1 upon 1 plus exp. So this seems to be okay with everyone. Derivation of the gradient for regularized logistic regression. Okay. Now what about the Hessian? So gradient is fine. What about the Hessian? Well, the same exercise you have to do once more. But now you'll have to look at all the interaction terms. Xi, Xj. Right? Those Xi, Xj terms will actually lead to this outer product. Xi, Xi transpose is what? Okay, Xi transpose is a matrix of x1 square, x2 square, x1 x2, x2 x1, right? All the interaction terms, they're products of the interactions of the cross terms. So if you expand it, you'll find that this part will just give you an identity, because only an I interacting with I will matter when you look at the W vector. And this part, very much similar to what we did earlier, you'll have the derivative of exp would ensure that exp remains, but the component that you're summing inside, you'll have to just take its respective terms out, the terms with those indices out, right? That's what we have done here. Okay. And then on top of that, so that's what happens here, sorry, xi transpose, only those terms from the inside the exp which are concerning I or j come out. The rest is just exp again, and the denominator remains. This is now there will be a square of 1 plus exp. So this is clear. I've just written now the same Hessian slightly differently. If you write sigma z, what is this called? The sigmoid, right? Use sigmoid, then basically the Hessian can be written as sigmoid of yi w transpose xi into this 1 minus sigma yi w transpose xi into xi transpose. Is this clear? There will be a lambda I sitting out from here. Okay. So now we look at convexity, and convexity will require a use of gradients repeatedly. So therefore, I think our background preparation will help. So why convexity? Well, every function has convex regions. It's not that there's a course on convex optimization. I should teach that in the past, but now we deal with convex regions of functions, and more invariably, a convergence of algorithms is generally in terms of convergence in convex regions. So convexity is something you need to understand anyways. Okay. So I try and depict this here. So if you have, even if you have a non-convex function like this, it still has convex regions, right? And you talk about most deep learning, where are the compositions of activation functions such as sigmoids, which I just showed in the last slide. Right? They will exhibit losses which are of this form, which have these regions, convex regions. So we'll look at projection methods. Convexity becomes important. In fact, convexity is very important for the sets. You will project into convex sets. So even if there's a point where there's no derivative, right, for convex regions functions at points of non-differentiability, you could still have subdifferentials or gradients. So we'll understand these in terms of supporting hyperplanes and so on. So one of the first theorems, first results I'll talk about without proving is the supporting hyperplane theorem. So this is like you'll have supporting hyperplanes at points of non-differentiability, and those will help you determine your so-called subgradients. Okay. Yeah. So the other thing is, if the domain constraints of optimization functions will be typically convex sets. So the domains are themselves convex sets. That's the other reason convexity is important. um, so you want to make sure that your all your subsequent iterates are within the same region, right? So convexity in the domain starts becoming important. So we'll quickly do convex sets and convex functions. Won't take too long. Okay. So the first is convex set. So set C is convex if for every 2 points x and y in the set, then the line, all points in the line segment lie within the set. Very easy to comprehend. Right? And the best way is to think of this. You have x, you have y, you have x and y, and this combination, which is going to be our favorite combination, lambda x into 1 minus lambda y for all. Okay. This is my set. So I want to make sure that for all lambda which are between 0 and 1, all points within that line segment lie within the same set. I mean, you can also have 0 less than equal to lambda, but that's a trivial case. Now, the other thing is if you have multiple convex sets, then their intersections are also convex, right? If I have one such set like this, another set like this. Now, if I consider this region of intersection, it is convex, and it's easy to prove, right? Because you need line segments within this, right? If 2 points are here, then line segment should be here within the first set, and line segment should also be within the second set. Is a union of convex sets convex? If I take this one and this one, union need not be convex. Because you'll have a problem. If you have a line segment like this, right? It won't lie necessarily within the set. So union need not be convex. Then projections. So I've been talking about I talked about projections when we did low rank matrix factorization, non-negative matrix factorization. You recall? Okay. So we'll recall. So in this case, I had to project right into what set? Greater than equal to 0. Right? I wanted to ensure that every component of L and R is say greater than equal to 0. So you could think of the entire space greater than equal to 0. Now suppose my solution was here. Right? What would I do? My projection would be, well, actually, the space is this one. Greater than equal to 0 mean all of these. So if my point is here, my projection would be normal, right? So that projection is in terms of finding a point in the set C. Let's call this a set C, such that the point y is the closest to x in terms of a particular norm. Okay. So this is typically the Euclidean norm. Okay. So projection of x into C is that element I in C that minimizes x minus y. And this is, as I said, typically the 2 norm. But you could also consider other projections. Behaviors are going to be, somewhat less intuitive. Yeah. X need not be in C. That's the whole point of non-negative matrix factorization, right? I'll end up getting some negative elements, and I want to project them into a set C, which is positive set space, right? So C is convex. Now, question is, if you C is not convex, what would you do? What does projection into a non-convex set mean? Sorry? So projection into a non-convex set need not be unique. Right? So if I say this C or, so union, right? Union is like or. So if I have this example, so these are two sets. Now let's say I have a point here which I want to project into the union of the two sets. So because the union doesn't contain this space, this is X. The projection is not unique. This is also PCX. So this is C1. Let's call it C1. And this is PC2X. So if I consider a union, both PC1X and PC2X are projections. You understand the intuition? So on the board, I only provide intuitions, no proofs. But yeah, some of these are important observations. If C is not convex, such as union, projection need not be unique. Yeah. Okay. So these are examples of convex sets: norm x less than equal to k, W transpose x less than equal to k, which are like hyperplanes. Norm x less than equal to k is specifically called a what? It's a norm ball. We'll see example. I mean, a norm ball. So if, in fact, I'd shown you examples, but norm x less than equal to k is called a norm ball. So if you look at the 2 norm, right? So this is a norm ball. But if you consider the 1 norm of x less than equal to k, how will it look like? How will this look like? Yes? Diamond structure? Simplex? Will it be a simplex? Okay, so 1 norm. 1 norm ball. This is also a norm ball. How do you think infinity norm ball will look like? How will it look like? Cube, yeah. So Right. So, but these are all going to be centered around 0. You could also put a center which is non-zero. Okay. These are zero norm, so zero centered norm walls. Now, if we have a convex function, we'll talk about convex functions, which really convex functions, cup shaped. Then it turns out that the associated set is also convex. Okay. But we'll just formally define convex functions a little later. Okay, so these are examples I showed you. Okay, union is not convex. We figured out the answer, and this is an example of one norm ball. I'm sorry, it's yeah. I showed that example in then projection I showed, and then this is a hyperplane. I didn't show this, the hyperplane, and so on. Okay, so now you may wonder if union is not convex, then can I make it convex? You could do the following. You could consider convex hulls, which is convex combinations of points lying within the set. Okay, so this is all possible convex combinations, which will basically mean that if the points were scattered here and there, you can create this hull, which is like looks like a polyhedron in this case, but need not be always. Like this was basically a you know a non-convex region whose convex hull is become convex, right? So should S be always convex to define a convex hull? Is it necessary for S to be convex? No, right? What are the convexity of the convex hull? It will always be convex. So now one homework I'm going to leave you with. We have 1 or 2 minutes left. So homework. So for convex sets, are you guaranteed to have something like a supporting hyperplane? Which means that no, original set, okay, let's distinguish these two sets, right? One set you had was like this. It was not convex. Now, if I try to come up with a supporting hyperplane, supporting hyperplane, what I expect is that every point, right? Not every point, but basically I can at any point I can come up with this hyperplane such that points on the other side are certainly outside the set. What else should happen with the supporting hyperplane? Should touch, right? Would we expect for convex sets the supporting hyperplane to be unique? For non-convex sets, would it be unique? Here's an example of non-convex set. Okay, so I'm going to leave you with a homework problem. Can you come up with the notion of supporting hyperplane? Obviously, you can read up definition, but apply your intuition a lot more. Right, and there's another homework I want to leave you with. Okay, so what about the convexity of the convex hull? So intuitively you feel it's all going to be convex, but can you verify it? If I take any convex combinations of points, lambda 1 x1 plus 1 minus lambda 2 lambda 1 x2. Now let's say this x1 and x2 were not in the original set, but they were in the convex hull. Right, so x1 itself could have been, you can see here, right? X1 itself could have been theta 1 y1 plus 1 minus theta 1 y2. X2 itself could have been theta 2 z1 plus 1 minus theta 2 z2. So how will their combinations look like? Get a little familiar, right, with compositions. That will be very handy. So in fact, you can verify that by substituting for x1 and x2 in terms of y1, y2, z1, z2. The new combination will still be convex in y1, y2, z1 and z2. Basically, you need coefficients who sum up to 1 in y1, y2, z1, z2. So leave you with those two homework problems. Yeah. Moodle. It's all on Moodle. Are you not able to see these on Moodle? So are you not on Moodle? Every class I've been posting on Moodle. Just give me a second. I want to make sure you're not. Moodle is place where we also posted the link to projects. You didn't get the link. And on Teams also I've been posting. So this is the Moodle page where I keep putting reference of lectures from previous offering. Right, I've been doing that. I put lots of reference materials. I keep referring to those as well. Then I'm also kind of recording these on Teams, so therefore you can probably see it for reference. But it's not going to be high quality. It's not meant to be capturing anything in the board. So it's just a cursory reference. So I've been recording it, and along with that, I put the slides. Just click on this, right? I mean, click on any of these. So okay, here if you just click on this, that's a slide. Okay, so oh, you are just viewing the videos, is it? No. So just click on this. This is a slide. So this is a slide of, and then what I do is also put the preparation for the next lecture. So I hope that format is helping. Okay, thanks. So I'm going to continue with the space.